So Jason's here. All right. So same thing as yesterday. We're going to be doing problems with Taylor series and learn how much fun we can have with them. Granted, I did realize once I made the post on Canvas that when I say fun, might be different than your definition of fun, but hopefully y'all think it's fun too. All right. So to warm us up today, I'm going to follow kind of the same pattern that we did yesterday. To give you all a recap of the problem that we did yesterday was to find a power series representation for it. Isaac, we're going to start off with a couple warm-up problems for 11.3, and then we'll dive into 11.4, in which the way I think of 11.4 in your book is, here's cooler stuff you can do with Taylor series. So I'll start with 11.3 to warm us up. But to give us a recap from a problem we did yesterday was, from our Taylor series for Maclaurin, we can always rewrite and make brand new power series using our properties of power series. And that's going to be the main goal of our warm-up problem, which will be oh, this will be fun. So for our warm-up problem, find the Maclaurin series of this guy. And also when you do that, find the radius of convergence and the interval of convergence as well. And I want to make a note that any method here is fair game. Meaning you can use our old faithful method to solve it, in which you just take a lot of derivatives to find those coefficients. Or you can use properties of power series that we know to rewrite a Maclaurin series for that guy. Give y'all about 340, 342 or something like that before we go over to solution. And this is going to be our warm-up problem. And as before, if you have a question, unmute your mic or post your question on the chat. All right, let's see that comment. Let's go ahead and do that. I'll respond to that message. All right, give me a status report, y'all. How are you doing on this problem? All right, since this is our warm-up, plan on going over the solution now. Does anyone want more time to work on it, or do y'all want me to go ahead and go over the solution? All right, well, don't see any comments. All righty. I'll go ahead and say that the answer that Luke got is correct. Actually, hold on. Actually, Luke, one comment on yours since I look. In your denominator, you just have k. I claim it should be 2k factorial in your denominator. And we'll see why in a minute. So my apologies for that earlier. So I claim that the solution overall is going to be from 0 to infinity, s to the 2k over 2k factorial. Let's see why s to k's. So we have e to the x plus e to the negative x over 2. And because I see e to the x power, I'm going to go ahead and use the fact that I know it's Maclaurin series already, which is s to the k over k factorial. All right, and with that, since I have a 2 in my denominator, the first thing I'm going to do is I'm going to go ahead and move that 1/2 to the front and only deal with the e to the x and the e to the negative x. Since I know the Maclaurin series of e to the x, I could go ahead and replace that with this Maclaurin series. And I'm going to replace e to the negative x with this next Maclaurin series. Because I have a negative x instead of just an x, what that means when I plug it in is I'm going to have the sum of k equals 0 to infinity like I've done before, but using our property of power series, wherever I saw an x originally, I replace it with that composition, negative x to the k power. So I have that going on. Meaning right now I have 1/2 times the sum k goes from 0 to infinity of x to the k power over k factorial plus the sum k equals 0 to infinity of -1 to the k power times x to the k power over k factorial. So right now that looks super ugly. Let's see how we can simplify to the series that we have that I claim will be as Maclaurin series. So I'm first going to expand the first terms in the series. K3 cubed over 3 factorial, and so on. And for the second series, if I expand out those terms, at k equals 0, I'll again have a 1. But because of that alternating term, and because my power is k, every odd term is going to have a negative sign up front. So I'll have a minus x plus an x squared over 2 factorial minus x cubed over 3 factorial plus ... to continue on. Now noticing that I could go ahead and kill out some stuff. Because of the second series is changing, alternating, where for every odd term, I put a negative sign up front. That means every odd term is going to cancel itself out. Whereas for the even terms, I'm going to combine them with like terms, but I have two of them. So I'll get 1 plus 1, which is 2, 2x squared over 2 factorial, and a 2x to the 4th over 4 factorial because they're appearing twice after cancellation. So my next step is 1/2 times combine like terms. 1 plus 1 gives me 2. Plus these two x squares gives me 2x squared over 2 factorial. And then if I had the x to the 4th power over 4 factorial, I'm adding x to the 4th power over 4 factorial to itself. So I'll have 2 x to the 4th power over 4 factorial, and that's where the pattern is going to keep on going. Add 2 to all the even terms remaining. We could simplify this further because of that 1/2 power, of that 1/2 in the front. I could distribute to all of them, and because I'm distributing that 1/2 to all of them, it's going to cancel out the 2's that appeared when I was combining like terms. Meaning I have 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial plus x to the 6th over 6 factorial, dot, dot, dot. I kept on going. Meaning my pattern that I have is that for every term in this series, I'm multiplying that k by 2, essentially saying I better have an even power and an even base in my factorial, which means my pattern will be x to the 2k power over 2k factorial. And there's our Maclaurin series for that guy. Any questions so far about how I got that from my Maclaurin series? Like I said, look, I apologize for before. I didn't see that your denominator had k factorial, not 2k factorial. All right, if no questions so far, let's go ahead and find a radius of convergence. Again, since we're now experts with power series, we know how to find the radius of convergence now. We're going to find the values for x that makes that series converge. Because I have a factorial, I'm going to try out the ratio test. So I'm going to list out a of k, which means I copy down what the terms in the series was. And a of k plus 1 tells me wherever I saw a k originally, replace it with k plus 1. Factorial. Let's simplify that real quick. If I distribute that 2 to that k plus 1 on both the exponent and within the factorial, I'm going to have x to the 2k plus 2 over 2k plus 2 factorial. Before I do the step 4 the ratio test, which is take the limit of the absolute value of those ratios, I'm going to go ahead and simplify the 2k plus 2 factorial or expand it so that way my cancellation step becomes a little bit more clear. Here's what I'm thinking of. Because in this factorial, my base is 2k plus 2, that means I'm going to start off at 2k plus 2, and when I multiply, I subtract 1 from it. So I'm going to rewrite that as 2k plus 2 times 2k plus 1, and then I'm going to leave behind a 2k factorial there. And I'm leaving it as 2k factorial on purpose so that when I do the step on the ratio test where I take the limit, it cancels out with that 2k factorial. All right. And now let's do L. Limit as k goes to infinity of ak plus 1 over a of k equals limit as k goes to infinity of what I've written as ak plus 1 simplified as to the 2k plus 2 over 2k plus 2, 2k plus 1 times 2k factorial times the reciprocal of the ak term, 2k factorial over as to the 2k power. Time to cross out is simplify. There goes our 2k factorials. And I get rid of the x to the 2k power, and I'm just left with that s squared in the numerator. Which means after cleaning up, I have the limit as k goes to infinity of the absolute value of s squared times 1 over 2k plus 2 times 2k plus 1. Because x squared is a constant with respect to my limit k, I get to take that out of the limit, and because I'm in the absolute value, I'm going to have absolute value for x squared times the limit as k goes to infinity of 1 over 2k plus 2 times 2k plus 1. But since that is positive, the absolute value is redundant. Because I have only k's appearing in the denominator and nothing appearing in the numerator, from our tools from Cal 1, that equals 0, which means the holding equals 0, which is always less than 1, which means my radius of convergence is infinity, and my interval of convergence is any real number that I could think of. All right, that concludes our warm-up for today. Now let's get to some more interesting stuff. But before I move on, does anyone have any questions about that problem? About how I got the Maclaurin series and how did I get the radius and interval of convergence for that series? Again, if you do, just post down in the chat or unmute your mic. Because now we're going to get to interesting stuff. Here's how I'm going to change it up on y'all. So there's a reason why I got y'all into the practice of using properties of power series to make a brand new power series, or use the Maclaurin series representation of functions that we talked about to make brand new series, because it's going to help us out with problems like yes. So what I want y'all to do next is using Taylor series I want you to evaluate the following. The limit as x goes to 0 of arctan of x minus x over x cubed. And again, I want y'all to try to do that with Taylor series, not with L'Hopital's rule or anything like that. Try to figure out, and the goal for this problem is, how can I use Taylor series to evaluate that limit? I'll give y'all about 10-ish minutes to work on it before we go over the solution. And if y'all have questions, again, post them on the chat or unmute your mic and ask me a question. For you, so I'll go ahead and write out the Maclaurin series for arctan. So y'all can use that to help y'all out. So there's our Maclaurin series for arctan to help y'all out with evaluating that limit. Gotcha. Out of curiosity, how many of y'all want me to go over this solution and then I help y'all and then y'all work on another one similar to that? Because this one could be tough at the very beginning of how to do these types of problems. All right. Alrighty. So I think for this one, I'll go over the how to do it, and I'll give one that's similar to try to evaluate. So what I'm going to abuse is a couple of properties for for power series. One property that I'm going to abuse is the x to the m power over a power series. Or I can move that x to the m inside. Let's see if I could cancel. So here's how we're going to do that limit. So the first thing I asked myself is, do I currently know a Taylor series representation for one of these guys? And the only one that I know of initially is the arctan. Because that s cubed is in the denominator for presentation, what I'm going to do is I'm moving that 1 over x cubed up front and having the arctan of x minus x. And that's mainly for what I'm about to do, so that we're not have to write super small. Because I know the power series representation for arctan, I'm going to use that now, which is the limit as x goes to infinity of 1 over x cubed times the series sine k to 2k plus 1 and then I have that minus x still there. So right now, that's not helping me out at all. So let's expand out that Maclaurin series to see what's going on. Also, is the limit going to 0 if not going to infinity? Let's make sure I can read it, write 0 there instead of infinity. It's cubed. All right, so when I plug in 0 for all of them, I'm going to get positive term, and I'll just get x minus, I plug in 1, I'll get 3 in that denominator, a negative sign, and a 3 in the exponent. Plug in 2, get 5 in the denominator. I'm going to get a positive sign, and I'm going to get 5 in the exponent. So s fifth over 5 plus or minus, and that's where the pattern is going to be. Plug in 3, I'll get 7 in the denominator, a minus sign, and 7 in the exponent, and the pattern keeps on going. Dot, dot, dot. And then I still have that minus x from before. From this, now I check and see. Inside the inner parentheses, can I cancel anything out? The only thing that seems like I can cancel is the x in blue and the x in pink, because I have x minus x. So those guys get to cancel. So my goal with the limit when I'm doing Taylor series with it is I want to see out the function. Let's summarize that. Which one do I know a Taylor series for? And then I expand it, and my next question, the step is, can I cancel stuff out? In this case, the only thing I could cancel out inside that inner parentheses is that x, leaving me with the limit as x goes to 0, 1 over x cubed negative x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus dot, dot, dot. And then my next step is I have a 1 over x cubed that I'm going to distribute to everything inside that parentheses. And what that's going to do is subtract 3 from all of those parentheses that I currently have. That's the limit that I'm taking after doing all of that work gives me negative 1/3 plus x squared over 5 minus x to the 4th over 7 plus x to the 6th over 9. And the pattern's continuing like that. And I say that we now win because I'm taking the limit of a continuous function, in this case a polynomial, meaning the limit is equal to plugging in 0 for x, meaning that this is equal to negative 1/3 plus 0 squared over 5 minus 0 to the 4th power over 7 plus 0 6th power over 9 ... Which means that I'm going to have 0 everywhere with the exception of that minus 1/3. Therefore, my limit at the very end is going to be a negative 1/3. And if you want to verify that that's right, note that we could use L'Hopital's rule here. And I claim that if we do L'Hopital's rule for that, we'll get negative 1/3 as well.
Would you mind scrolling back down a bit?
Yeah, sure thing. Tell me when to stop.
Yep, you're good.
Okay.
Okay, thank you.
No, you're welcome. All right. And there's going to be your game plan to try to get that guy and to get that limit. So that's going to be our general strategy. Let's try to do that with another problem. So kind of using the similar structure that we did for that problem. Use Taylor series to evaluate the limit as x goes to 0 of natural log 1 plus x minus x plus x squared over 2 divided by x cubed. And again, I want y'all to try to do this problem with Taylor series, not with L'Hopital's rule or any of the other tools that we have. And ask yourself kind of the same thought that we had when we did this problem. Which one do I know a Maclaurin series or a Taylor series for? After I expand a Taylor series, is there stuff that I can cancel out? Is there stuff that I can distribute? And then after you do all those steps, evaluate the limit. So try that for that problem. Figure out which one we know Maclaurin series for. And again, I'll give y'all until 4:20 p.m. If y'all have any questions, post them on the chat or unmute your mic and let me know. All right, give me a status report, y'all. How's this problem going for y'all? Gotcha. Keep in mind, Luke, that if you want, you could use the chart at the end of section 11.3 if you want to reference that. So with that, I'll give you all a few more minutes to work on it. Like I said, if you have a question, let me know. Or if you think you have the answer, also let me know. Oh yeah, if you still want to figure it out, Luke, go for it. And if you need questions on figuring out that Taylor series, also let me know. All right. So give me a status report, y'all. How's the problem going? Luke, you said you're still trying to figure out the Maclaurin series for natural log of 1 plus x. All right. Out of curiosity, what did y'all get for the limit of this problem? Give y'all a few minutes to type out your response before I go to the solution. Okay, well, let's go to the solution. So just like before, taking the limit as x goes to 0, because that x to the cubed power is in the denominator, I'm going to move that up to the front as 1 over x cubed. So that's natural log of 1 plus x minus x plus x squared over 2. And what did we get for the Maclaurin series of natural log of 1 plus x? Give y'all a minute to type down what the Maclaurin series of natural log 1 plus x is while I take a sip of water. Bingo. The sum going from k equals 1, bingo. Because if it was 0, I'll have denominator 0. Of negative 1, k plus 1, x to the kth power over k minus x plus an x squared over 2. All right, so let's now expand our Maclaurin series to see which terms get to cancel out. The limit as x goes to 0 of 1 over x cubed. When I start at k equals 1, I'll have 1 plus 1, 2, so that means I'll have a positive 1. I'll have a 1 in the exponent and a 1 in the denominator, giving me just x. Plug in 2. I'll get 2 plus 1 equals 3, so I have an odd pair with the negative 1, meaning I'm going to have a minus, and a 2 in the numerator, in the exponent, and 2 in the denominator, giving me x squared over 2. And the pattern is going to be that for every even term, I'm going to have a minus sign up front. Dot, dot, dot. And I have a minus x and a plus x squared over 2. And I'll put parentheses here to make it clear that that's going on forever. And so because of this, I have a plus x and a minus x, popping in. Oh, let's close those parentheses. Which means those x's are gone. I have a minus x squared over 2 and a plus x squared over 2. So those two are gone, leaving me with the limit as x goes to 0, 1 over x cubed. And then I just have all of this left over now. So x cubed over 3 plus x to the 4th, or minus s to the 4th over 4, can't read, plus x to the 5th over 5, minus x to the 6th over 6, and so on. And so from here, what value am I going to get for the limit? If I distribute that 1 over x cubed over, then evaluate the limit, what will I get at the very end? Bingo. I'll just get a 1/3 as my final answer for that problem, because the only one that will not have an x after distributing will be the very first term. All right, and there's our fun time with trying to take limits using Taylor series. So now the next series of problems that I want to try to practice on is using Taylor series to take derivatives of functions that we know about. And for that, these series of problems, I'm going to use the following property for power series. Is that if I know a power series can be represented as a function, then if I take the derivative of the function f of x, what I can do is I'll take a derivative of that power series, and what my property of power series tells me is if I take a derivative of a power series, I could take the derivative term by term, which in other words tells me the derivative gets to come inside my series. And I take derivative of that. And since they're polynomials, I use power rule. So it's going to be the sum, not from k equals 0, but for k equals 1 of k times c of k times x to the k minus 1 power. Keep in mind that I'm starting at 1 now, not 0, because at k equals 0, I just have a constant, and a derivative of a constant is 0. So that's going to be the property that we're going to be using for the next series of exercise problems. And so I'll do the first one, and then I'll give you all other problems to work with. So what I'm going to do is say we're going to confirm that the derivative of e to the x is boring, in which case the derivative is itself, using Taylor series. Let's go about that. Taking the derivative of e to the x. I know it's Maclaurin series, which is d dx of the sum from k equals 0 to infinity of x to the kth power over k factorial by my property of power series. I can move the derivative inside the power series to give me the sum from k equals 0 to infinity of the derivative of xk over k factorial. The k factorial is a constant with respect to x, but I'll take a derivative with respect to xk. So by my property above, I can rewrite this as the sum k starting at 1 to infinity of k times xk minus 1 over k factorial. And if you want to follow along with that formula or that pattern in purple, I see if k here is the 1 over k factorial portion. But let's go ahead and start simplifying. I have a k factorial, I have a k. I can rewrite k factorial as following. As k times k minus 1 factorial, meaning I could cross out that k, and I have now k minus 1 factorial. So now I have the sum going from k equals 1 to infinity of x to the k minus 1 over k minus 1 factorial. So I'm not necessarily done yet because I want the if I want to prove my claim that derivative of e to the x is itself, I want the Maclaurin series of e to the x to pop up, which means my series needs to start at 0 and not at 1, and to fit in that form. And so now what I'm going to do is, how can I force that guy or my sum to start at 0? And if you were here a few days ago when I talked about this, y'all know what my game plan is. I'm going to do something called a change of variables. And what that means is I'm going to define a brand new variable, and then I'm going to use that to rewrite my series in terms of that brand new variable. And my goal for doing this is I want the series to start at 0 so that I can fit into the form for the Maclaurin series of e to the k power, of e to x. And so because I have k equals 1, well, that implies that k minus 1 equals 0 if I subtracted both sides by 1. And that's going to be my motivation for me defining my brand new variable, which I'll call L. I'm going to define my brand new variable to be L, which equals 2k minus 1. Meaning, when I go back to my series, k equals 1 to infinity of x to the k minus 1 power over k minus 1 factorial, because I'm doing a change of variables, I'm going to rewrite the entire series in terms of my brand new variable L. And doing that gives me the sum from L equaling 0 to infinity. And then now within my series, wherever I saw a k, I do need to rewrite this in terms of L. In this case, since I have just k minus 1 appearing both in the exponent and in the base of the factorial, I just get to write an L. And now I have a series starting from 0 to infinity, x raised by the index L over the index factorial, which is our Maclaurin series representation for e to the x. And therefore we showed, using Taylor series, that the derivative of e to the x is e to the x. So that's going to be our motivation for using that series of problems. So using that same methodology, I want y'all to evaluate the derivative of negative cosine of x using Taylor series. And y'all note that the derivative of this should equal to sine of x. So you know that when y'all do this, in the end, I do need the Maclaurin series for sine of x to pop up at the end. So what I want y'all to try to do is use Taylor series to try to take the derivative of negative cosine of x and see what y'all get. Give y'all a couple minutes to work on it, and then we'll go over the solution together. Like always, if you have a question, post them on the chat or unmute your mic and let me know. Can you clarify that, Luke? I don't quite get what you mean. I see. So the reason why I wrote that in pink is to let y'all know that y'all should know what the end goal is. So what the goal is to just use Taylor series to confirm our intuition from before. So that's what I meant when I wrote that. I wasn't trying to assume that it was sine of x. I was just clarifying to y'all that you know what the end answer should be. So if we get something wrong, we know that we messed up somewhere. That was what I was trying to do. I get what you mean with the circuit argument thing now. So that was me not clarifying it. So sorry about that. Did that make sense? That was why I made I mention about the just derivative equals sine of x is we know our end solution should be. I wasn't trying to make that circular argument, so my bad. Not quite, because we know the Maclaurin, because I'm assuming we know the Maclaurin series for cosine. Oh, I understand what you mean, Luke. You're talking about when you take the first derivative of that when you're trying to form the Taylor series. Okay, I gotcha. The goal for you. Okay, I get what you mean. What you meant now with your question. Another way to rewrite yes is the goal is to evaluate yes using the Maclaurin series. For cosine of x. So I should have added that for more clarification. So that's my bad for not figuring out what you interpret until just now. So I should have written that for more clarity of what I meant. Yeah, so for yes, I'm going to assume that y'all know the Maclaurin series for cosine. Like I said, sorry for not understanding what you meant with your question first. Yeah. All right, I'll give you a few minutes to work on that. I'll be right back. One of my roommates asked me for something. right. Luke says that he's got it. Isaac and Matthew, how are y'all doing on this problem? All right. So since it's close to 5, let's go ahead and go over the solution. So first thing I'm going to do, because I have a constant in that derivative, I'm going to take that constant out before I do anything else. Now using the Maclaurin series for cosine, I have sum going from k equals 0 to infinity of -1 to the kth power x to the 2k power over 2k factorial. All right. Because I'm taking derivative of a power series, I get to use my property of power series that says I get to move that derivative inside the power series and take derivative term by term. So now I'm taking the derivative of, let's write that in blue, -1 to the kth power, x to the 2k power over 2k factorial. Now, oh, there we go. Ah, crap. Get back up there. There we go. All right. And so now I want to take derivative term by term, meaning this becomes written as minus the sum going from k equals 1 to infinity of -1 and 2k factorial are constants. So -1 to the kth power. And then I take derivative of 2k s to 2k power by the power rule, which will be 2k times x to the 2k minus 1 over 2k factorial. I'm now going to use the fact that 2k factorial is 2k times 2k minus 1 factorial to rewrite that as just 2k minus 1 factorial in a denominator to give me negative the sum from k equals 1 to infinity of -1 to the kth power times x to the 2k minus 1 over 2k minus 1 factorial. And because I have that negative sign up front, I could technically move that inside to give me k plus 1 for that. All right. And because my series is starting at 1 and not 0, I'm going to have to do a change of variables or whatever makes that equal to 0. In this case, that's going to be L. So I'm going to let L be k minus 1. which means inside the series, wherever I saw a K, I'm going to have to rewrite that in terms of L. And unlike the previous example, I don't have just a K minus 1 popping in, meaning I can't rewrite, just go ahead and say, oh yeah, it's just L. So we're going to have to do some rewriting to rewrite the K plus 1 and the 2K minus 1 in terms of L. So because L equals K minus 1, what that's going to do is L plus 1 equals K, which means L plus 2 is going to equal K plus 2. K plus 1. So K plus 1 is taken care of now. Now, I'm going to have to take care of the 2K minus 1. First thing I'm noticing, if I multiply L by 2, it's going to be 2 times K minus 1, which is 2K minus 2 after distributing, which means for me to get to 2K minus 1, I'm going to have to add, oh, nope, that should be another minus 1. What am I doing? There we go. That means I'm going to add both sides by 1 to give me a 2L plus 1 is going to equal to the 2K minus 1 in my sum right now. And now with that scratch work done, I can rewrite the sum from K equals 1 to infinity of negative 1 to the K plus 1 power x to the 2K minus 1 power over 2K minus 1 factorial as the sum from L equals 0 to infinity of negative 1. We rewrote K plus 1 as L plus 2. X to the 2K minus 1 power becomes, based on our scratch work, X to the 2L plus 1 over 2L plus 1 factorial. And that plus 2 and a negative 1, I'm not worried about it because that's just negative 1 to the L power times negative 1 squared. But this negative 1 squared just gives me 1. That'll just become negative 1 to the L power. Meaning I can simplify this further as the sum going from, go away, of L from 0 to infinity of negative 1 to the L power times x to the 2L plus 1 over 2L plus 1 factorial. And that, my friends, is the Maclaurin series for sine of x, which is what we expected and what we should have gotten. All right. Yeah, QED or do that at the end. That's what modern mathematicians do, to just draw bots to end the proof. Fun fact, when I was an undergrad, my professor said that we could end a proof with whatever we wanted. And so I ended in my homework assignments my proofs with a Pokeball because I was a very smart aleck person from undergrad. Yeah, when you say you can use whatever you want to end a proof, I'm like, nice. I'm going to do that. So, yeah.
Well, that was fun. I have a quick
Yeah.
question.
Yeah, go ahead, Isaac.
Would you mind once again scrolling up to the top? I missed the first two lines of that. Negative D. Oh, it was literally okay. That makes
Yeah.
sense. And all right, yeah, that's really all I needed. Thank you.
Alrighty, you're welcome. Any other questions about the take-home quiz or anything else? If not, thank y'all for coming. I will see y'all on the flip side.